we're going to finish up the packet today, and then next week what'll take place is I'll give you a review sheet that'll cover most of this stuff. It'll be very, very similar to the type of things that you should expect to see on the test. We'll have more dimensional analysis information on the test. So if you did really well on the quiz, you're sitting well for the test that's coming up on Friday. Okay, everybody will take the test on Friday. All right, so let's go ahead and get started with this classification of matter. And it's funny that I say that matter is made up of stuff because we're being real vague. I'm not getting into the specifics yet. We'll talk about the stuff that actually makes that up. But do realize that if you have something, you have matter, including light. In other words, and some people would argue and say, you know what, light isn't made up of matter. Actually, light does have weight. It's a photon. It's really, really small, but it does have some weight associated to it, and it would be considered matter. So again, matter is the stuff of which the universe is composed of. And I mean, there's a lot of stuff out there that the universe is composed of. And it has two characteristics. It has mass, and it occupies space. Okay? Even the air that we're breathing right now has a mass, and it's relatively heavy, thank goodness. Because if it weren't, bad things would be happening to our bodies right now. There are three states of matter. Hopefully you all know this: solid, liquid, and gas. And everything on the periodic table, and this is the AP periodic table, but it's still the same thing. Everything on that periodic table can exist as either a solid, liquid, or gas. You could exist as a solid, liquid, or gas. Just depends on how much heat is present. All right, hopefully we'll never get to that vapor stage or that gas stage. All right. If it does, well, it was nice knowing you. Okay? All right, physical and chemical properties and changes. When we talk about physical changes mean that it simply goes from one state to the other, like either a solid to a liquid or to a gas, or from a solid to a gas. However, what's really neat about a physical change is, like for example, water. If I take solid water, which most of you commonly call ice, and I add some heat to it, it turns into a liquid, which we like to drink. Add some more heat to it, it's now a gas or steam. But in all three of those cases, it's still H2O or water. That's the definition of a physical change. When we talk about chemical changes, if I start with water and I chemically change it, what's water made up of? Hydrogen and oxygen. Good. And those are two things that are normally what at room temperature? Are they a solid, liquid, or gas? Gases. So I have two gases that actually make up that liquid. And that's one of the things about chemical properties is that when we take two things and combine them and actually put them together chemically, they have totally different properties. Like for example, table salt. Who in here likes table salt? I love it, on pretzels especially. I mean, I'm not asking you to chug it or anything. It's not a cinnamon challenge. But the thing is, with sodium chloride or table salt, it's made up of sodium and chlorine. Okay, and if we were actually able to chemically pull those two apart and have a sodium atom and chlorine molecule, we'll say, if I were to take that sodium atom and place it in water, does anybody know what would happen to that? It would explode. Okay? If I take pure sodium, and I've got a video I can probably show you guys a little bit later on, but if you take that pure solid sodium, place it in water, it'll explode. Okay? We'll talk about why that does. And then if I look at the other component there, the chlorine gas, if you're in the presence of chlorine gas, nothing but chlorine gas and some oxygen, it's toxic. You could die. So here's a situation. I could have a container of sodium chloride, stick two electrodes in it, run an electrical current through it, and actually cause those things to, quote unquote, decompose into solid sodium and chlorine gas. Well, as that's taking place, if you're standing over that and you're allowing that process to take place, so the chlorine gas starts to be generated, you inhale that, you pass out. As you pass out, your face hits the container containing the pure sodium, you start drooling, now your face catches on fire. What a great way to go. However, I really like sodium chloride. It tastes good on my food. Okay? Different because it's how it's combined. All right? So when we undergo chemical changes, you start with one thing. So for example, if I were to take this paper, put a match to it. I'm not going to do it because I like these notes. If I put a match to it, it changes into some black substance. In other words, it'll burn away some of the components of the paper and leave the carbon behind. That's what the black is. However, when we talk about physical changes, I can take that solid water, make it a liquid, and then a gas, and I can capture that gas and do the reverse. However, if I take this piece of paper, light it, burn it, can I get it back to paper? No. It takes quite a few years. I could actually take the carbon, sprinkle it under a tree, let the tree absorb that, and then cut the tree down and got paper again. Okay, but that's going to take a while. So there is a nice recycling. We actually just keep moving things around. So chemical changes, take one thing, change it. I think that's enough with the chemical and physical changes. Let's talk about properties. When we talk about physical properties, okay, and it says on here, are properties that do not change the chemical nature of the matter. For example, like the color of something. Again, if it's a physical property, like for example, I had this set up for AP chemistry. This is cobalt chloride. When you guys take AP chemistry, you're going to find out that certain metals have different colors when they're ions. Cobalt has this nice green hue. Now when I take a look at this, and it's kind of nice, this is food coloring. Now I use this for a demo, but they look pretty much alike. So I'm curious if the food coloring has some cobalt in it. But again, I don't know the toxicity of the cobalt, so maybe not. All right, but that change, or that color will not change as I go from a solid to a liquid to a gas, as long as I have that in solution. Some other things that don't change, the physical properties, the smell, okay? Generally, the warmer something gets, can you smell it better or not as much? Better, because once you start heating stuff up, it starts generating those gases. Yeah, so if you want to keep something from not stinking, keep it cool. Okay, that actually slows down the metabolic decay rate and all that other stuff. So smell, if it's a dead thing we're talking about. Freezing point, boiling point, regardless of what state it's in, it still has that same temperature at which it freezes at or boils at. Not going to worry about the infrared. All right, chemical properties. These are properties that don't change the chemical nature of the matter. So, for example, like the heat of combustion. Certain things burn better than others. Okay, whenever we talk about something burning, that's a chemical process. Okay, heating so much that it changes it from a solid to a liquid to a gas is not a chemical, it's just a physical change. Some physical properties may be divided into extensive and intensive properties. Extensive properties are things like mass and volume. Okay, so this is a volume of around 1,000 milliliters or 1 liter. Okay, that's an extensive property. And this is of water. We'll pretend that the food coloring is not in there. It won't change the boiling point by any great amount. But intensive properties don't change regardless of how much we have. So does anybody know what temperature water boils at? Celsius, of course. 100, good. So let me ask you a question here. If I had this amount of water, okay, it's about a liter, and say I go over to the swimming pool and it has the same kind of water, doesn't have all the chlorine and everything in it, which of those two will boil at a higher temperature? The water here or the water in the swimming pool? The water. They boil at the same temperature, right? It's water. Water. Okay. So they boil once the temperature gets to 100 degrees. That is an intensive property. Now, here's the follow-up question. Let's say I take a Bunsen burner and put it under this container, and then take a Bunsen burner, same size, same amount of heat, put it under the swimming pool. Which one's most likely to boil first? This one. That's an extensive property, okay? So the mass of this, or the volume of this, is much, much smaller, so there isn't as much to heat up. So extensive, mass, volume, length sometimes, those can change. Intensive properties, you are what you are, all right? So the boiling point and freezing point won't change regardless of how much we have. It might take a little longer for it to heat up or cool down, okay? So does that make sense with intensive and extensive? Let's see. One more problems. Oh. Man. All right, elements and compounds. And we're almost done, unfortunately. I know that bums you guys out. Aren't we almost done? Maybe? All right. Elements and compounds. Who can tell me the difference between an element and a compound? Or are they the same thing? They're not the same thing. Good. Okay. Say it again. Okay. And an element it is what it is. It's the smallest thing that we can break down. In other words, I can take a compound like sodium chloride, break it down into sodium atoms and chlorine atoms. I can't take a sodium atom and break it down anymore. If I do, what type of reaction am I undergoing? Not a chemical, but a nuclear. Yeah. Okay, so if I break down a sodium atom and remove some protons and neutrons, I'm changing that atom. So when we talk about elements, it's the smallest unit of matter that can be broken down under physical conditions, okay? Not nuclear conditions or chemical reactions. Compounds, some compounds are really simple, some compounds are really big. Like when you get into organic chemistry, there's some compounds that can have over 100 atoms attached to it. I think your DNA is a great example of that. It's got some atoms attached to it. Okay, so we'll talk more about the elements and compounds, and actually, when we get done with our last test, I'm going to give you the elements names and symbols that I want you to memorize. But we're not doing compounds yet. So some examples of some molecules or compounds: oxygen gas, sodium chloride, magnesium oxide, and then that thing. You don't need to know what that is. That's an organic thing. Actually, that right there is glucose and nitrogen gas. Did you guys know that was glucose?
Yeah.
C6H12O6. It's a sugar. Let's see. And here's the other blank, one kind of atom. Characteristics of mixtures and pure substances. When we talk about a mixture and something that's pure, if I have a block of sodium chloride, okay, you know those big blocks that the cows can lick? Any farm boys or girls in here? You know what I'm talking about? Good, okay. If that substance is made up of only sodium chloride, can we consider that a sample of pure sodium chloride?
No.
Yeah. Okay, if there's nothing but sodium chloride, we can say that's pure. Same thing with water. And again, I want you to use your imagination for a moment. Ignore that this is not green. If I only have water in here, do I have pure water?
Yes.
Yeah. Now, water, again, is a compound, H2O. So oftentimes when we think about something being pure, we often think that it can only be an atom, but it could be a compound as well, as long as there's nothing else in there. If there's something else in there, then we consider that to be a mixture. All right. So, like for example, some of you might have brass faucets in your bathroom. Okay. Brass is not pure. Brass is made up of nickel, copper, some cobalt, some iron, some other things in there to give it that brassy look, whatever it's called. But that's considered to be a mixture. And mixtures can either be a gas, like what we're enjoying right now in this room. And does anybody know what air is mostly made up of? What is it? Nitrogen. About 79 point something nitrogen. What comes in second place? Oxygen, thank goodness. And then what comes after that? Carbon dioxide, good. Then there's some water vapor and some other stuff in there. So that would be considered a mixture as well, because we have all these different gas molecules. Okay, it's not pure. We don't have pure air. I don't know what that is. Okay, so if it's one kind, whether it's a solid, liquid, or gas, it can be considered a pure substance. And it doesn't have to be just a single thing. Oftentimes we refer to like, oh yeah, I got pure gold. Okay, well that's one kind of atom. Okay, but I also could have pure sodium chloride, which is just sodium chloride in a compound or in a block. Does that make sense? Maybe? Oh, what are you saying? All right, solutions, the last thing, unfortunately. This would be considered a solution. Okay? This would be considered a solution. Okay? So you have two examples of solutions. This would be considered a mixture. Okay? So again, a solution looks like this, a mixture looks like this. Now can somebody, and it's dirt with water. That's yummy. Okay, what can somebody tell me the difference of a mixture and a solution is, just based on what I'm doing right now?
So a mixture makes
Good, good, good. Go on. Is that all you got?
Like the solution, they don't separate.
Nice. In other words, when I look at a solution or an example of a solution, no matter how hard I shake this up, it still looks the same. Okay? If I were to walk in this room and I know it's made up of air, I'm hopeful that it's made up of air, I can't say, all right, sorry guys, you're not getting any oxygen because I'm taking it, I'm hoarding it. Okay? No oxygen for you. It's up for us. Okay? In a true mixture, in a true solution, okay, it's evenly dispersed throughout. Okay? In a mixture, it's not evenly dispersed throughout. Now, let's say that, hopefully this doesn't open up. As I shake this around, okay, yummy. Okay? As I shake this around, there's some sand, some dirt, some water in here, and as soon as I stop shaking it, what happens? All the heavy stuff goes, boom, right to the bottom. Okay? And as I look at this, I'm going, wow, that's a pretty mud color. That's really nice. But my question to you is, will this look like this an hour from now?
No.
If I keep shaking it, it will, so I'll have to put work into it. So, if I come back a little bit later today, maybe on Monday Tuesday whenever we meet again, it'll look like that again. Okay? And what's really cool, and I don't think you guys can see the different silt lines here, there's actually some nice algae growing in there. Ugh, nice little biosphere. But these will not remain like this, say an hour, a day, a week, a year later. Okay? So if I probably shouldn't have done that, I have class next hour. Crap. Oh well. So there's another one. I'm not shaking that one up. But that is an example of a mixture. I come back a week from now, a year from now, however long, this is still going to look like this because everything's evenly dispersed throughout. The food coloring's not going to settle out, which is nice. That, by definition, is a solution. What is this? Water with green food coloring?
No, I said, will it evaporate? Does water evaporate?
If I take the top off, yes. Good point. Yeah, it would definitely, if I left this alone without the top on there, it would definitely evaporate. And then what would be left in here? The food coloring. Excellent.
What's the little tube thing at the top?
What tube thing?
Like that.
We'll talk about it later.
Oh, well, I didn't know if stuff could have
Good morning.
Good morning.
Yeah, so that was for AP, a demo that I had there. But again, a solution here, everything's evenly dispersed throughout here, so it's not going to change in that regard. All right, here's another example. Had a student make this up a couple years ago. It's oil and water that somebody put some food coloring in there. It's kind of gross as you move it around. Nasty looking. Is this a solution or a mixture?
Mixture.
Why?
Because it's not evenly separated.
Exactly. So if I shake it up, looks like a nice little smoothie. Yeah, I wouldn't drink it because it's vegetable oil and water, so it looks kind of gross. However, this is mixed up for right now, but before we leave, probably got about a half hour or so, you're going to start to see some separation. We'll talk about why that separation occurs is because they don't like each other, number one. Oil and water are different. Don't want to talk about why just yet. Okay? Actually, I do have one more thing back there. It's not as exciting as... Now, this might disturb some of you. Look at that. Isn't that exciting? I made this flask my first year of teaching 15 years ago. Okay? It's the same as this. Now, there's a little more food coloring in here. However, this is a great example of a solution. This is 15 years old. As long as I don't take the top off, it's going to look like this 15 years from now. Yeah, that's a good example of a solution. I didn't have to shake it up to get it to look like that. It's going to stay like that. Okay? So, that's the difference between a solution and a mixture. Any questions? All right, for tonight, do the fives. That's it. That's your homework. And if you get it done, you got a half hour-ish.
What's this table thing about, though?
Oh, the table? Oh, okay. Let me show that real quick. No, it's not homework.
It's not homework.
No, it's not homework. This table here, this is all the metric prefixes that I know about. Okay, you know, like yada, or yoda, or whatever. Okay, the only ones that are in bold, those are the ones that you guys are responsible for. Yeah, so the Great Mega King one, yeah, these are all the ones that exist, and I think I even said it on the first day. There's more, but these are the only ones that you need to know. So if you want to go home and impress your friends, I guess you could do that, but yeah.
No, we can make up some other.
All right. So, and you have that on, I think, the last page, so that's there for you. Any questions about like physical and chemical differences? Do you want to do the first one of each one?
Yeah.
Okay.
Put them all together.
No, we won't do them all. I want you to have some fun. Let me actually, I'll pick 2 from each one. How's that? Is that good? Okay. All right, let's look at 5A, unless you guys want to do them yourself. Okay. All right, 5A says, classify each of the following changes as either a chemical or a physical property. Okay. All right, let's see here. Growth of a plant, is that physical or chemical? Okay, hold on. Before you answer, make sure you know what you're saying. Because again, if it's a physical change, you start with one thing, and as it undergoes from a solid to a liquid to a gas, it's still the same thing. Now, trust me, I love plants, and I think it'd be really cool if they were able to go from a solid to a liquid to a gas. But the growth of a plant, what's happening? Yeah, it's actually growing. How's it growing? It's pretty complex. We're not going to get into that. Photosynthesis is a big contributor. Very good. And actually pulling nitrogen out of the air and some of the carbon out of the air helps that plant to grow. Also, the dirt really helps it to grow.
Can we just write like a C or a P?
That's fine. You don't care. You just want the answer. I get it.
No, I care.
All right. Let's find another one here. VII. Where, here?
Yeah.
Ferments? Ah, you know that one. I'm not going to tell you that.
Just V.
V?
P.
This one?
No.
What's,
VII equals P, right?
what are you saying? V? You're saying VII equals P?
I'm saying the question.
Oh, you're giving me the answer. I don't know. We'll wait and see. Let's do this one. All right, a solid piece of lead is placed into a vat of molten lead.
That's P.
Physical or chemical?
Physical.
Why?
Because it's both of it's like the same thing, lead, but just one solid and one just one.
Okay, so if I place, I'll do it on something that we do every day. Let's say I take a glass of water and place an ice cube, which also happens to be water, in that cup. What happens?
It'll melt.
Melts. Okay, so the ice cube will melt. All right. So is that a physical or chemical change? Physical. Yeah. Yeah.
That is physical.
So that would be physical as well. Lead is lead is lead. All right. Let's look at the next one. Next section. B. Uh-oh.
There's other ones that I don't know.
All right. Classify the following. I'm looking at 5B here. Classify the following properties as either chemical or physical.
This paper is white.
This paper is white. Is that a physical or chemical?
Physical.
Physical. Very good. Water vapor condenses when the molecules strike the side of a cold glass of iced tea.
Physical.
Physical. Good. So it changes from one thing to another. Good. No, you don't know that song. Don't do that. All right. That's your homework. All right, 5C. Classify the following properties as either extensive or intensive. Okay. What does extensive mean again?
Such as intensive doesn't change.
Intensive doesn't change regardless of how much we have. So that was the example of the boiling point.
Depending on mass of
How big it is or how small it is. Good. So Ductility, in other words, the ability to bend easy, is that a intensive or extensive? Intensive, very good. Okay. Now, as I make it longer, it makes it easier, but there's a certain ductility value for certain metals. Density, intensive or extensive? Intensive. Okay. Regardless of how much I have, it's going to be that same mass per cubic centimeter. Okay. Yeah. Okay, so if I have, say, a block this size, the density is still the same. How many grams per cubic centimeter? Or a block as big as this room. The mass per centimeter cubed is still the same.
Oh, okay, so that.
All right.
What did you say, like mass and length? What did you
Density
say?
is not mass and length. That's actually an intensive
What
problem.
did you say mass was?
I didn't say.
Oh.
That's your homework.